Okay, I think I'm ready to go now. I just got an email from one of our alert students out there, and she said, "Hey, I think the pre-lab isn't due September 19th." Oh, genius is born every day. I am such an idiot. Yes. I'm sure the other 17, I've noticed about 17 or 8 of you have already logged in and started doing it. I'm sure you all noticed, the others noticed that too. I fixed the due date. It is February 17th now. And now it goes away February 23rd. So you gotta stay on top of it. And we'll get this one done today, hopefully. It seems like this is taking me forever to get done. But in this lab, okay, we're going to find out how much power we generate. And so in the first 2 videos, you saw how we measured the stairs and how we measured our time running up there. And so here's the big ideas behind this. Work is the change in kinetic energy of the system. So you need a stopwatch, a ruler, a step, 20, if you can find them. A good place to do it, and especially with the extremely mild, extremely almost scary mild winter we've been having. A flight of steps at the side. For those of you that are working adults that are living out in the suburbs or in town somewhere, at a high school, you can run those steps, or have one of your kids run the steps. All right. So you measure the height of one of the steps. Count. I showed you how to do all that, and then the work you've done when you run up the steps is against the gravitational attraction of the Earth to your body. The work is your mass times gravity times the height of the steps, and your stopwatch will tell you how long it took, and plus so the amount of work that you did, you're also going to add, not only are we going to add the work you did to overcome the pull of gravity, we're going to do the work that the average speed, the average kinetic energy that you burned getting up the stairs. Okay, and we're going to do that. So your final report contain the following data: the rise of one stair, run of one stair, calculated diagonal length of one stair. So that way I can get my average speed, and I'll show you. That's probably the trickiest calculation we're going to do. All right, and so and then the number of stairs, total height of the stairs, convert to meters, total diagonal distance of the stairs, convert to meters, calculate your mass if you don't want to do that, gravity. And so the power is your kinetic energy plus the gravitational energy divided by the time that you went up the stairs. All right, so let's take a look at my data real quick. Okay, so let's take a look at what I was saying, what I did. All right, so this is going to work. I think I'll just keep this all as one thing. So for my first trial, and I think I have you do 5 trials here so you get an idea. All right, so my first, I measured that the height of the stairs was 17 centimeters. Height of one stairs was 17 centimeters. Okay, number of stairs was equal to 21. So my height in the y direction, in other words, I ran up 21 as such. Okay, so this was 17 and this was 30. 17, 30, 17, 30, 17, 30. Okay, kind of like that. All right. Okay, so then I'm also going to have to calculate this diagonal distance here, which we will do. Okay, so the height would be 21 times 17 centimeters, which we can do in our head pretty quickly. We go, oh, that's 357 centimeters, which is equal to, divide by 100, 3.57 meters. Okay, so that's the height. All right. Let's see. Well, let's say my mass is 110 kilograms. Okay, there's my mass. All right. Now, the diagonal distance that I went up would be 17 squared plus 30 squared. And then I'll take the square root of that. 17 squared plus 30 squared. That's 1189. Take the square root of that. And that's 34 inches for one step. 34 centimeters is the diagonal distance for one step. Well, I went 21 of them. So again, the diagonal distance, so you take the square root of all that, I wound up with 34 centimeters. So my diagonal distance is 21 times 34 centimeters. And again, you can do this in your head. That'd be 300, that'd be 68 times 10, which would be 680, plus 34, which would be 714. Let's just see if that's right. 21 times 34. All of a sudden, 714 centimeters. And so my diagonal distance in meters is 7.14 meters. Now, here's the deal. I ran that 7.41 meters in, according to my watch here. Okay, so I look at my stopwatch, and here was the time that it took me to run that distance, 7.93 seconds. Okay, so I ran, so my average speed, which is what we're going to use for my kinetic energy getting to the top, would be 7.14 meters per 7.93 seconds. Meters per second gives me the speed. So I'm going to take that, oh dear. So I'm going to take 7.14 meters divided by 7.93 seconds, and that's a very slow 0.9 meters per second. When we saw, well, I guess my physics is smart, we saw that at times Usain Bolt was running, he averaged 10.4 meters per second. Of course, he's running on flat ground. Of course, he's a world-class athlete, too. I used to be. No, not even close. So then I'm still going to use that time. So I have my time is equal to 7.93 seconds, okay, for that first trial. And then my kinetic energy would then be 1/2 my mass times my velocity squared, 0.9 squared. That's my kinetic energy. Then my gravitational potential energy is equal to my mass times g times h, where we found out g in the last lab was 2.98 meters per second squared. Okay, and my mass is 110. So for me, the total work for me to get up those stairs was equal to do the 1/2 again, to do the 1/2 calculation, I do 0.5 times 110, which was my mass, times, and I put this in parentheses, 0.9 squared, boom. So 44.5 joules plus, that's a joule, that's a J, plus this would be 110 times 9.8. So right away, this thing's huge. This is over 1,000 joules, is right there. Times the height that I went up, which is 7.1, no, 3.57 meters. Whoa, 3,848 joules. Almost knocks this out. I mean, this is barely 1%. This is barely a little more than 1% of that. But we'll go ahead and keep it. And so I add those two together, plus 44.5. And I get 3892.96, which I'm going to just say is 3893. 3,893 joules divided by, now my power will be the joules, the change in joules divided by the time. So I got 393 joules divided by, what was it, 7.93 seconds. is equal to 490, almost 491.9 watts. Wow, that's pretty cool. And then my horsepower, I kind of look like a Clydesdale. Let's see what my horsepower is. So my horsepower would be 490 watts. Let's go 491 watts times, is it 0.00158? What was our conversion to horsepower over here? Oh, it's in my lab sheet. That's right. Now we go to horsepower. 1 horsepower is 744 watts. So I divide by 748 watts. In other words, 1 horsepower. In horsepower, here we go. Let's go back to this. So the horsepower, question mark, the horsepower would be times 1 horsepower per 745 watts. So I get 491 divided by 745 equals 0.65 horsepower. Let's go with 0.66 horsepower. 0.66 horsepower. Okay? I'm a half a Clydesdale. That even sounds worse than I made old one. All right. So anyway, that's how you do the lab. Enjoy it. I think you'll get a kick out of it. And out here.